So before we go any further with our discussion of the consequences of this approximation methods we've been talking about, we need a way to measure the error in our results. And if you've taken a science class at any point, these formulas are probably familiar because they're the exact same ones you use in science classes. We're going to define we're going to define the error to be just the difference, the exact value minus the approximation. The absolute error is the absolute value of that, so it's just the magnitude of the error. And to get the relative error, we'll take the absolute error and divide it by the exact value. Okay, so let's look at an example of this. If you remember from the last lecture, we calculated using our approximation method. We took 5.4, converted it to an approximate machine number. Then when we converted that back to a decimal number, this is what we ended up with. All right, so this is our floating point approximation of 5.4. You notice that it is an approximation, it's not exact. Okay, so what do we get with these different errors? Well, the error is just the difference of the two, which comes out to this number here. And if you remember from the previous lecture, I did this calculation. Remember, I said I did this in MATLAB, and it didn't come out to 0, which obviously you would reasonably expect. And the reason was these approximations that take place. But now looking at this, if you remember that lecture, you might look at this and say, well, wait a minute. Those numbers are not the same. The differences are not the same. Why is that? Okay, well, the answer is converting 5.4 to 5.00, so on, that required one approximation. Doing this arithmetic operation down here, first the 5.4 had to be approximated. Then, okay, 5 is an integer, 5 is a machine number, there wouldn't have been any approximation there. But then we had to do the subtraction, so the result of the subtraction had to be approximated. 0.4 is not a machine number, so that has to be approximated. Then the second subtraction gets an approximation. So there were actually 4 approximations that took place over the course of doing this single little arithmetic expression. And what you're seeing here is the net result of all of those approximations, some of which may have gone up, some of which may have gone down, some of which may have been bigger or smaller or whatever. So that's the cause of this variance that we're seeing here. All right, so finally, right, the absolute error is this. It's just the absolute value of the error. And to get the relative error, I'm going to take the absolute error, divide by 5.4, and we get this number. Okay, you might be feeling good about this, right? Because, I mean, that's pretty small. Obviously, we'd like it to be 0. We'd like it to be exact, but we know it's not going to be. And 10 to the negative 17th is a pretty minuscule error. Well, I hate to be the bearer of bad tidings, but it gets worse. So what we're going to do in the next lecture, we're going to dig a little deeper into this, and I'm going to demonstrate some specific combinations. And it's not like this stuff is really common, right? That these errors are cropping up all over the place. But they do happen, and you need to be aware of them. So that's what we're going to look at in the next one. I'm going to look at some examples where these errors are a little more substantial.